An interstellar comet named 3I/Atlas has swung into our neighborhood on a one-and-done, hyperbolic path, and the vibe is equal parts thrill and should I be worried? Earth is basically a rock that won the cosmic lottery. And now the lottery office just sent an auditor. Consider this NASA science, plus one twist of cosmic mystery. The headline is simple: this traveler is not from around here. It is not bound to our sun. It is not looping back for a reunion tour, and it will not be joining the family reunion out past Neptune. It is a passerby with its own story, and we just caught it mid-monologue. Chapter 1. The Visitor with No Return Ticket. Let us unpack the hyperbolic part in plain words. Most comets that belong to our solar family move on long, stretched ovals, slingshotting out and back like a loyal boomerang. A hyperbolic path is different. It is the track of a sprinter who never turns around, only leans in for a quick hello, and then vanishes into the dark. That shape tells you about energy. If you have more than the minimum energy to be held by the sun's gravity, you are free. The comet's speed and direction say it is a free agent, probably nudged out of its home system ages ago by a giant planet, then buffeted by the thin tides between stars until it wandered into ours. Interstellar travel, not glamorous, very slow, but undeniably epic. Spotting one of these is like hearing an accent at a party and realizing your guest arrived from a different continent entirely. Astronomers see it in the numbers of the orbit, in the angle it approaches, and in the subtle way sunlight plays off its growing halo. There is a brief, golden window for observations. This thing brightens as it nears the sun, shedding gases that make a glowing coma and tail, and then it fades again. The clock starts the moment we notice it. Cue the observing frenzy. Telescopes across Earth scramble, the big space observatories get penciled in, and backyard astronomers start warming up their cameras like fans before a playoff game. Good evening, curious minds. Science doesn't need to shout to be fascinating. Sometimes it's best enjoyed the way you'd enjoy a late-night conversation, quietly, with a cup of tea, and maybe the soft hum of a fan in the background. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new as you drift towards sleep, consider subscribing. No pressure, only if you enjoy these calm journeys through the universe. Now, let's begin. Why the fuss? Because interstellar comets are time capsules from other star systems. They formed under rules similar to ours, but in a different neighborhood with different ingredients and different weather. Each fragment of dust is a postcard from somewhere our spacecraft have never flown, and every color we see in the tail, every whisper of gas we detect, is a hint about the kitchen where that cosmic recipe was baked. Photosynthesis is plants saying they invented solar panels first. Comets are deep space ice chests saying they invented freezer storage before anyone had a kitchen. Open one carefully, and you can taste the early universe, metaphorically. Please do not lick the comet. There is also the drama of uncertainty. Early images look fuzzy, because they are. Comets are surrounded by their own fog machine. The nucleus hides inside that glow like a candle in a paper lantern. We infer size, spin, and texture by watching the light flicker, and by reading the spectrum, which is like a barcode of elements and simple molecules. Think of it as astrophysical forensics. You do not see the culprit directly. You reconstruct the crime from footprints in the snow and a cup of melted ice on the table. The first few nights of data are a rush of maybe and seems like, and then with more eyes and more wavelengths, a clearer picture forms. Meanwhile, the public narrative tilts between wonder and worry. Will it hit us? Short answer, no. Long answer, also no. But with extra syllables and a diagram, the hyperbolic path is a flyby, not a bullseye. Disaster movies promise a space rock with an attitude problem. This is more like a celebrity tour bus passing through town. You could get a great photo. Your roof is safe. Still, there is a healthy seriousness in the air, because even a harmless interstellar visitor tests our systems. Can we spot fast movers early? Can we coordinate observations across continents? Can we extract the maximum science from a brief encounter? Planetary defense is not just about deflecting doom, it is also about practicing attention. Here is the part I love. Encounters like this reshape our sense of home. Most days, the solar system feels like a walled garden. The big planets are our trees. The asteroid belt is the gravel path, and the Kuiper belt is the fence at the edge of the yard. An interstellar comet is the neighbor leaning over that fence to say hello. And also, by the way, your fence is mostly polite fiction. Space is porous. Material flows from star to star over unimaginable spans of time. The galaxy is not a collection of sealed apartments. It is a neighborhood with a slow, patient breeze. So we stand under the night sky, look up, and try to make the most of a short meeting. We will watch the tail breathe under sunlight. We will listen to the spectrum for the hiss of water vapor, the sweet signature of carbon compounds, the dust that tells us how grains stick and shatter. We will compare the story to the two famous interstellar guests that came before, and we will not rush to label this one as ordinary or strange. Curiosity first, then humility, then better questions. Black holes are the universe saying delete browsing history permanently. Interstellar comets are the universe dropping a mysterious file on our desktop and walking away. In a few months, it will dim beyond the reach of most telescopes and return to the great between, but it will not leave us empty-handed. It will leave refined techniques, better teamwork, and a sharper instinct for the next surprise. The chain reaction begins with wonder, and the second link is preparation. Onward. Next time, we will rewind to the moment of discovery and tell the story of how a small, suspicious speck turned into a headline. Chapter 2 will take you through the first week of observations and the clues that shouted, "This visitor is not from here." Chapter 2, how we spotted a stranger in a crowd. The discovery began, the way many cosmic stories do, with a small, suspicious dot that refused to behave. In the Chilean night, one of the asteroid terrestrial impact last alert system telescopes swept a wide field of sky like a lighthouse, taking rapid images a few minutes apart. Most dots were well-mannered stars, staying put because the telescope tracks the sky's rotation. A few dots slid gently from frame to frame. Those are our local pebbles and snowballs. But then came the oddball, a fast mover with a direction and speed that made the software blink and the humans sit up. It had the wrong kind of path, the kind that quietly says, "I came from out there." Consider this NASA Science +1, with the +1 being the many unsung steps between a blip and a headline. Surveys like this are built for pattern recognition. First, the pipeline subtracts one image from the next, erasing the steady wallpaper of stars and leaving only things that change, moving points, new flashes, a sudden flare. The computer links these appearances into a tiny sequence called a track, essentially a motion doodle across the night. For a garden-variety asteroid, that doodle lines up with what the sun's gravity would do to something in our neighborhood. For this object, the doodle whispered a different story. The angles did not match standard family shapes. The speed was just a little too ambitious. It was like watching a school of fish and noticing one fin slicing against the current. The alert zipped out to the global community. Here is a candidate. Please confirm. This is the moment when astronomy becomes a relay race. Observers across longitudes point their instruments and begin to pin the newcomer's position against precision star maps. Each measurement is a tiny thumbtack on a celestial corkboard. Plot enough thumbtacks, and you can trace the curve, and the curve tells you what kind of traveler you are dealing with. A familiar member of the family will sketch an oval, maybe a very stretched oval, but still a loop that closes. This object refused to close the loop. The curve bent outward like a highway ramp that never rejoins the circle. What, in simple language, makes a path interstellar? It comes down to energy and shape. A bound visitor is like a roller coaster car that climbs and dips, but always remains on the track. An interstellar visitor has a ticket that frees it from the ride entirely. When you fit the motion with the best model of the sun's pull, the shape is not an oval at all. It is open. The object is moving fast enough, that the sun cannot keep it. It will drop by for a brief hello, then keep going into the deep. That open shape, together with the inbound direction that does not line up with the outer comet reservoirs we know, is the signature of a stranger in a crowd. Confirmation is not just one telescope nodding. It is many eyes, many wavelengths, and a blizzard of careful checks. Observers look for earlier, overlooked images, so-called pre-covery shots that might have caught the visitor when it was fainter. Digging up those older frames lengthens the timeline and sharpens the story. Others check for false positives, satellites we mistook for rocks, hot pixels, cosmic rays that photobombed a single exposure. You do not want to crown a cosmic visitor and later discover you knighted a glitch. The Minor Planet Center collects the reports, runs orbit fits, and posts refined solutions as the points stack up. With every additional night, the uncertain cloud around the path shrinks, and the open-ended shape asserts itself more boldly. There is a human texture to this process that I love. Someone in Chile catches the odd motion before sunrise. Hours later, someone in South Africa or the Canary Islands snags the next positions. A researcher wakes to a coffee cup and a fresh set of coordinates. An amateur astronomer with a modest scope and sharp software nabs a few more points that tip the math in favor of the interstellar verdict. It is science as a world-spanning group chat, where the only emojis are real photons. Why does this classification matter? Because interstellar is not just a label, it is a passport stamp that promises unique science. A local comet tells us about our own cold storage. A visitor from the space between stars tells us how other kitchens stocked their shelves. The angle of arrival hints at the lanes that drifting objects follow through the galaxy. The inbound speed hints at the pushing and pulling it endured before we met it. Declaring an object interstellar changes what instruments we point at it, which questions we ask, and how quickly we move. You do not leisurely stroll when a limited-time guest is crossing your foyer. You sprint for the microphone. There is also a practical twist. A fast, unbound object stress tests the whole detection network, linking moving points, assigning priorities, scheduling follow-up time on crowded telescopes. This is the dress rehearsal for the day, when a more urgent object barrels through. The procedures sharpen. How quickly can we release positions? How reliably can we filter out the fakes? How gracefully can we hand off observations across hemispheres and weather windows? You can measure the health of a planetary surveillance system by how smoothly it handles a cosmic curveball. Back to our oddball. Once the open path became clear, the name followed, and so did the scramble for deeper looks. Color measurements, early hints of a halo, and the first clues to rotation. But those belong to later chapters. This chapter is about the moment of recognition. The crisp, almost musical instant when the data stop sounding like background noise and strike a new key. In the background hum of routine detections, one note rang out, "Not from here." If you think of the night sky as a crowded station, discovery is not about shouting at every passerby. It is about noticing the traveler who carries a map from another country. Surveys like the one in Chile are our station guards and tour guides rolled into one. They spot the unfamiliar, send a message down the line, and invite the rest of us to look closer before the crowd closes in again. The stranger keeps walking. We keep learning. Next time, we will shift from the how to the what. Size, spin, and speed. Chapter 3 will peek behind the glowing fog and ask the practical questions. How big is the nucleus? How fast is it turning? And what about this visitor? Made even veteran observers say, "Wait, how big?" Chapter 3, Size, Speed, and the Wait. How big? Moment before you can fall in love with a cosmic visitor. You ask the same questions you would on a first date. How big? How fast? And what are we actually looking at under all that sparkle? With this interstellar traveler, those questions lit up the observing logs. Early images showed a lively glow, not just a shy pinprick. The first estimates whispered that we were not dealing with a pebble. This looked chunky, and that coma, bright, structured, and eager. It is the cosmic equivalent of a tourist arriving with 3 suitcases and a fog machine. Let us start with size, because that is where the how big moment landed. Astronomers do not measure a nucleus with a cosmic ruler. They infer it from brightness. But brightness is a sneaky witness. A bare rock will tell one story. A rock wrapped in a halo of dust and gas tells a louder one. So the trick is to peel back the light. Observers model the coma's contribution, subtract the glow from the neighborhood around the nucleus, and ask what would be left if you could switch off the fog machine for a second. That back-of-the-envelope process is like estimating the size of a campfire by staring through its smoke. You can do it, but you learn to love uncertainties. Albedo enters the picture next. How reflective the surface is. A dark, charcoal-like nucleus needs to be larger to reflect the same amount of light as a lighter, frostier one. Because we do not know the true reflectivity at the start, early size estimates come in pairs. If it is dark, then it is this large. If it is bright, then it is smaller. With this object, even the conservative scenarios refuse to shrink it into a tiny shard. The models leaned towards sturdy snowball rather than skinny sliver. Mass is even trickier. No one is dropping it on a scale. Instead, we infer mass from size and a guess at density, which depends on porosity and composition. Comets are famously fluffy, more meringue than granite. Push that through the mental calculator, and you get a mass range that is not precise, but is good enough to frame the story. Plenty of material to drive a healthy coma, enough heft that sunlight alone will not toss it around like a leaf. That is important because it separates true shape changes in the coma from optical illusions caused by jittery motion. Now about that speed, interstellar visitors travel with a kind of built-in swagger. Their inbound pace is set by ancient gravitational shoves and the long glide through the space between stars. When we talk about fast here, we mean fast enough that the sun does not get to keep the guest. Even so, there is a spectrum. Some visitors lope in, others sprint. Early tracking of this one drew a clean picture. Not the wildest sprinter in the galaxy, but absolutely in the fast lane compared to our garden variety comets. Speed matters because it shapes the show. Faster motion shortens the observing window, stresses telescope schedules, and sharpens the contrast in the coma as jets replay in quick time. The coma itself became the headline because it popped early, bold, and photogenic. Some comets play hard to get, waiting until they are close to the sun before they throw off a proper veil. This one seemed comfortable, lighting the stage from a respectable distance. That tells you something about surface layers and the inventory of ices. If the top crust is fragile or cracked, sunlight can work its way in and start the geysers sooner. In pictures across multiple nights, observers saw not only a general haze, but hints of structure, subtle asymmetries, slight fans pointing in consistent directions, like the comet cleared its throat and the microphone caught it. This is where the inevitable comparisons arrive, because we have 2 famous interstellar reference points. First, the enigmatic visitor that slipped through years ago like a rumor. Long, thin by inference, oddly featureless to cameras, and no clear coma to comfort the comet purists. That object sparked debates about fragments, pancake shapes, and everything short of, did someone design this? The absence of a visible coma made size estimates a high-wire act because brightness had to be tied to the body alone. In that case, every assumption about reflectivity carried extra weight, and every small uncertainty mushroomed into arguments at conferences. Then came the other celebrity, the one that acted much more like a classic comet. Bright halo, clear tail, textbook behavior under sunlight. That one felt like a confirmation that interstellar does not automatically mean strange. It smelled like ordinary comet physics, just from a distant pantry. Against that backdrop, our current visitor plants itself somewhere interesting. The nucleus reads as chunky rather than wafer thin. The coma arrives early and looks lively, and the overall energy says, I know this dance. It is familiar enough to anchor models, but distinctive enough to make observers refresh their coffee. There is a practical payoff to this size-speed coma trifecta. A bigger nucleus means more rotational inertia, so changes in jet activity create subtler wobbles. That steadier spin makes it easier to map the timing of brightening and dimming, which in turn reveals where the active patches are. A vibrant coma from the start gives spectroscopists something to chew on, because more gas and dust means richer signals to decode. And a firm inbound speed, well measured over consecutive nights, lets navigators predict where to point the big guns with confidence. In short, the first week's numbers shape the whole campaign. Of course, early estimates are provisional by design. As days pass, the coma evolves, the phase angle changes, and the glare at different wavelengths shifts. Teams update their models, swapping placeholder values for tighter constraints. The wait, how big moment becomes a refined statement like large enough to matter, small enough to study in detail, which is scientist, for we are thrilled. The goal is not a single dramatic figure. It is a living portrait that grows sharper as the visitor sweeps through the light and then fades into memory. So yes, a tourist with luggage and stage fog, moving briskly, carrying enough mass to strut without stumbling. That is the silhouette we are left with, and it is a good one. Next time, we will step into the glow itself and talk about what powers the halo and tail, how sunlight sculpts the show, and why color changes can read like a chemistry diary from far away. Chapter 4: A Tale of Ice and Sunlight. If you want to understand a comet's glow, picture a freezer that accidentally wandered into a tanning booth. Sunlight does the heating, ices do the reacting, and the result is a self-made spotlight that follows the traveler like a rock star on tour. Plants say they invented solar panels first. Comets say they invented special effects. The physics is surprisingly down to earth, warms something that has been cold for a very long time, and it vents, sighs, and throws glitter. Start with the surface. A comet is a mix of dust and ices buried in layers, like a frozen lasagna baked during the early days of a star system. Far from the sun, it is quiet as it drifts inward and the light grows stronger. The outer layers begin to warm. Water trapped in the pores loosens. More delicate ices, such as carbon monoxide and carbon dioxide, wake even earlier because they evaporate at lower temperatures. The pressure from these gases finds cracks, weak seams, and sunlit slopes. Then come the jets, focused outbursts of gas that carry fine dust with them, blasting from vents like tiny fire hoses. These jets carve the fuzzy shroud we call the coma, a cocoon of gas and dust that can grow bigger than a planet while remaining ghostly thin. Why a tale? Two sculptors are at work. One is sunlight itself. Light pushes on dust, gently but persistently, nudging the finest grains away from the sun and fanning them out in a graceful curve that traces the comet's recent path. The other sculptor is the solar wind, a stream of charged particles flowing outward. That wind grabs the lightest, newly freed atoms and molecules and sweeps them into a straighter, narrower tail that points almost directly away from the sun. The result is a two-part performance: a soft, curving dust tail that looks like a brushstroke, and a slender, more rigid gas tail that behaves like a windsock. Many photographs show both at once, crossing like ribbons. Inside the coma is where the chemistry sings. Sunlight is not just a heat lamp, it also acts like a set of scissors. Photons slice apart fragile molecules, creating fragments that glow at very specific colors when they relax. Observers with spectrographs, prisms with attitude, spread the glow into a rainbow and search for those fingerprints. A classic example is a carbon-rich fragment that paints the coma green. That emerald tint becomes more pronounced as the comet approaches the sun, because there are more photons around to snip chains and excite those fragments. Closer still, the green may fade in the tail, not because it disappears, but because those fragments break again into pieces that emit at different, subtler colors. Comets are drama queens. They love a mid-show costume change. Color changes are more than pretty. They tell us about layers. Early on, when the comet is far out, the first material to wake is often the more volatile stuff. things that vaporize with just a gentle nudge of warmth that can yield a bluer, cleaner-looking coma dominated by gas with little dust. As the sun's energy soaks deeper, heavier, dustier layers stir, and the coma can thicken and redden slightly as tiny rock and organic grains flood the halo. If you watch night after night, the palette evolves, an artist swapping brushes as they move from sketch to oil painting. Variations over a single rotation can also betray active regions. Imagine a lighthouse beam, but made of gas, briefly brightening one side of the coma as a jet turns into view. Jets themselves leave signatures in the shape of the coma. A single strong vent can sculpt a fan, like someone blowing flour from a baking sheet. Multiple vents can create overlapping shells, spirals, or faint striations that drift outward as the nucleus spins. Time-lapse imaging brings these patterns to life, revealing the rhythm of the engine within. In some comets, sudden outbursts spike the brightness by a factor of several in a single night, as a cliff collapses or a pocket of gas finds a new exit. In others, the show is steady, a slow exhale instead of a cough. Each behavior hints at geology without the need to land a probe. Cracks, boulders, slopes, and the strength of the crust all leave their fingerprints in the fog. The dust tail is its own detective story. Grain size decides how each particle responds to sunlight's push. Tiny motes get shoved hard and peel away in graceful arcs. Larger crumbs lag behind, tracing thicker, more sluggish curves. By modeling those curves, scientists back out the distribution of grain sizes and even the roughness of the grains. Smooth, glassy particles scatter light differently than fluffy, clumpy ones. These differences become clues about how the comet originally formed, whether its dust was forged in gentle sticking of small pieces or in more violent regroupings. There is another, subtler glow that sometimes appears, a faint yellow sodium tail, born when sunlight shakes loose atoms from dust grains, which then shine at a specific warm color. It is like catching the quiet chorus beneath the main melody. Spotting it requires dark skies, sensitive instruments, and patience. But when you do, it adds a layer to the soundtrack. Not just which gases are blowing off, but how the dust itself is weathering under the relentless stream of light. From a practical angle, the brightness of the coma is both a gift and a challenge. It makes the comet easier to detect and study, but it also hides the solid heart. To peek inside, observers use clever tricks, measuring how the brightness changes as the comet turns, isolating wavelengths where gas is dim but dust is bright, or the reverse, and taking high-resolution images that deconvolve the blur into sharper features. Think of it as astrophysical portrait retouching, except the goal is not to smooth features, but to reveal the bumps and freckles. All of this spectacle is powered by a simple thermostat: distance to the sun. Move inward, and the special effects team gets a bigger budget. Move outward, and the stage lights dim, the jets quiet, and the fog thins. Yet even as the show fades, it leaves behind a trail of dust that can seed gentle meteor showers years later when Earth crosses the path. The comet has left town, but the confetti occasionally drifts down long after the parade. So the next time you see a photograph of a comet with twin tails and a halo that looks like an illuminated cloud, remember the machinery behind the magic. Sunlight is the drummer, rotation sets the rhythm, vents provide the solos, and chemistry writes the color palette. Plants can keep their solar bragging rights. Comets will take the award for atmospheric effects. Up next, we follow the traveler on its route through the inner system, mapping the turns and explaining how timing and geometry shape what we can and cannot see from our backyard stage. Chapter 5, Course Through the Inner Solar System. Imagine a road trip where the driver refuses to take the same exit twice. That is our interstellar traveler threading the lanes of the inner solar system, a measured glide by the realm of Mars, a graceful dive toward the sun, and then a confident merge into the outer highway, past the giant planets, without so much as a glance in the rearview mirror. It is a one-way itinerary written by gravity and timing, and it reads like a postcard, wish you were here, cannot stay. Start with the approach to Mars. Picture the red world as a patient bystander standing near a crossroads. Our visitor does not buzz the rooftops, but it passes close enough that orbiters and rovers become an audience in the balcony. From that vantage, Mars gets an early look at the coma's glow and the angle of the tail, like catching the opening number before the house lights come up for everyone else. For people on Earth, that Mars moment matters for a simple reason: geometry. Where the comet is in relation to the Sun, and to us, decides how bright it appears, how long we can track it each night, and whether its tail draws a neat line away or a grand arc across the sky. Space is a dance floor, and the view depends on where you stand. After the Mars crossing, the road bends sunward. This is the swoop, the part of the trip where the dial turns up. As the comet descends into stronger light, its surface warms and vents punch through with more confidence. The coma swells, the dust tail becomes more assertive, curving along the path like chalk lines marking a runner's stride. Meanwhile, the gas tail lines up almost straight away from the Sun, a slender banner telling everyone which direction the stellar wind is blowing. The closer the visitor comes, the faster everything changes. Night to night, the head grows brighter, the tail lengthens, and the color balance can shift as different ices wake and different dust grains take flight. It is the quarter of the movie where the soundtrack goes from whisper to drumbeat. Now, about risk. This is not an impact threat. The path threads safely through the inner lanes. On the cosmic scoreboard, this is strictly a flyby, which is both comforting and slightly disappointing for anyone who secretly enjoys a good disaster montage. Keep the popcorn, no heroic asteroid wrangling required. The most dangerous thing about this event is the number of hours of sleep lost by observers chasing clear skies. If you want peril, you will have to settle for the mild hazard of stepping on a telescope cable in the dark, which, to be fair, is a rite of passage. As the comet sweeps by the Sun at its nearest point, the road tilts upward again. The visitor climbs the gravity well, trades some speed for distance, and heads toward the neighborhoods of the giant planets. Here is where the plot gets strategic. Those giants are not just landmarks, they are bouncers and shepherds. A very close pass with any of them would twist the path, but our traveler does not thread those needles. It keeps a respectful distance, skimming the outskirts of their influence. That means the long-term story stays simple. No sudden capture, no looping detour, no surprise round two. The object enters, performs its sunward pirouette, and exits stage dark. For sky watchers on Earth, the outbound leg can be just as intriguing as the approach, partly because the viewing angle flips. Early on, we tended to see the sunlit side, like a car with headlights facing us. After the turn, we often view the darker side, and the tail may appear to switch direction because our perspective changes, even though it still points away from the Sun. Season, latitude, and local time suddenly matter a lot. One night, the comet sits low in the dawn, barely above a purple horizon. A week later, it may ride higher in the evening, a faint brush mark beneath a familiar constellation. The trick is to think in 3 dimensions while moving, which is why every good viewing guide includes simple phrases like "look east before sunrise" or "look southwest after dusk." The sky is grand, but your neck still has limits. Timing also rules the chance of a naked eye sighting. When the comet is closest to Earth, it might not be brightest because it could be tucked into twilight. When it is brightest, it might be closer to the Sun from our point of view, sliding through glare like a firefly in headlights. That is why some comets receive applause for photographs, but only shrugs in person. Cameras are more patient than retinas. Still, there is magic in trying, especially from a dark site where the Milky Way looks like brushed smoke, and you can let your eyes adjust until the scene blooms. Bring a friend, bring a thermos, and bring the mindset that the hunt is half the reward. Past the orbit of the giants, the stage lights dim, the coma relaxes, the tails shorten, and the visitor resumes its true personality, a silent, sun-resistant speck, carrying souvenirs from a distant nursery. It will leave behind a faint ribbon of dust along its lane, a breadcrumb trail thin as breath. Years from now, those crumbs may contribute to a subtle whisper of meteors for someone else under some other sky. But for us, the headline is the route itself, a proof that interstellar traffic is not rare legend, but occasional fact. The map is open, the lanes exist. We have only begun to learn how to read them. So savor this itinerary, a nod to Mars, a deep bow toward the sun, a courteous wave to the giants, and a confident exit. No world-ending theatrics, just a precise, beautiful journey plotted by gravity and revealed by patient eyes. Next time, we will step away from maps and dive into motives, why a single visitor can trigger a cascade of actions here at home, from dust stream studies to policy meetings and new mission ideas. In other words, the quiet start of a chain reaction. Chapter 6. Why Scientists Whisper Chain Reaction. Every big cosmic visitor arrives with a suitcase full of questions, but the most important change begins after the photo ops. The first link is curiosity, the next links are action. When scientists whisper chain reaction, they do not mean a dramatic movie montage of blinking red lights. They mean a quiet cascade that spreads from observatories to boardrooms to classrooms, altering what we watch, what we build, and how we plan for the next surprise. It starts with dust, drifts into atmospheres, ignites new mission ideas, nudges policy, and ends with fresh hardware, pointing up with renewed purpose. Space rarely kicks down the door. It leaves the door ajar and lets our own momentum do the rest. Begin with dust streams, the most literal trail a comet leaves behind. As the visitor sheds grains, those crumbs trace its path like confetti from a parade. Over months and years, gravity and sunlight sort that confetti by size and push it into lanes. If Earth later crosses one of those lanes, the sky may pay it forward as a meteor shower. That possibility becomes an item on research agendas. Map the grains, forecast the timing, and estimate whether a mild sprinkle or a brief storm could happen in seasons to come. It is part weather report, part archaeology. The practical angle is not just romance. Meteor storms can charm stargazers, but they also nudge spacecraft designers to ask whether delicate surfaces and star trackers need extra shielding during peak nights. Space is beautiful and slightly sandblasty. Now to atmospheres, because even a thin drizzle of particles can tingle a planet's air. When a dust grain skims into an atmosphere, it vaporizes and seeds layers with extra atoms that glow under sunlight, and sometimes it triggers faint ripples in charged regions far above the clouds. On Earth, that might translate to subtle changes in radio communication or a night skyline that brightens for a few days. On Mars, or at the edge of a giant planet's magnetic bubble, it could mean a brief, measurable tweak that teaches us about how those environments respond to outside nudges. Think of atmospheres as musical instruments. A passing dust stream is a tap on the strings. Scientists listen for the note and learn how the instrument is tuned. Those two scientific ripples feed the next wave. New mission proposals. A lively interstellar visitor is like a memo from the universe that reads, "Please be ready." Teams sketch rapid flyby probes that can hitch a ride on existing rockets and sprint to intercept if the timing is right. Others design slow, patient surveyors that loiter in space, waiting for the next alert. There are concepts for tiny chip-scale cameras that could be launched in fleets, and concepts for nimble, solar sailcraft that can pivot across lanes faster than traditional engines allow. Suddenly, conference hallways hum with whiteboard math and elevator pitches. The question stops being whether we should try and becomes how to be ready when chance finally smiles. Meanwhile, policy people join the conversation. A single interstellar event can expose weak links in how the world coordinates observations and shares data. That nudges agencies to make timelines. Who issues alerts? How quickly do we publish refined paths? How do we prioritize telescope time during a narrow window? The policy shift is not the loud bang of a new law. It is the steady tick of updated guidelines, shared dashboards, and standing agreements between institutions. Planetary defense offices sharpen playbooks not only for impact threats, but also for rapid characterization campaigns, where the goal is knowledge, not deflection. Emergency response for science. The only siren is a telescope scheduler's phone. Education and outreach ride the same wave. When public interest spikes, classrooms lean in. Museums refresh exhibits. University programs pitch new courses that braid astronomy with data science and hardware. Students who are on the fence about a research track jump in because the sky just sent a personal invitation. One visitor, many career arcs. Curiosity has excellent word of mouth. Then we arrive at the spike in telescope upgrades, which may be the most concrete link in the chain. Every time a fast, unusual target races through, it stresses our gear. Astronomers jot notes during the scramble. We needed wider fields to catch more of the tail in one shot. We needed faster detectors to freeze fine jets. We needed a different filter to isolate that faint emission. After the dust settles, those notes become grant proposals. New cameras with lower noise, software pipelines that link moving targets more quickly, robotic mounts that can slew from horizon to zenith without a hiccup. Even giant facilities benefit. Sharper adaptive optics, better infrared sensitivity, and coordination tools that let many telescopes act like one organized choir instead of a room full of enthusiastic soloists. Space teachers, we upgrade. Do not forget the quiet revolution in data. A rare object catalyzes better archives and smarter automation. Teams build unified portals where positions, spectra, and images land in near real time. Machine learning models get trained on the oddballs so they can flag the next one faster. In plain terms, fewer wild goose chases, more premium goose. The tempo of discovery quickens a little, and once you increase tempo, people tend to keep it up. You can feel the tone change across the community. Before the visitor, interstellar objects were a chapter near the back of the textbook. Afterward, they sit closer to the front, not because they dominate, but because they test everything else we do. They are pop quizzes for our instruments, our coordination, and our imagination. They also remind us that the solar system is not a sealed terrarium, but a crossroads. When a crossroads reveals itself, travelers adjust their maps. The beauty of this chain reaction is that it rarely resets to zero. Dust models persist. Policy remains tighter. Instruments stay better. Missions proposed in the glow of one encounter may launch in time for the next. Curiosity starts the line of dominoes, but it is habit that keeps them falling in a useful direction. Space sends a nudge. We build a tradition. Next time, we will chase the first and most tangible link in detail. How dust streams evolve into future meteor showers, how to predict them, and what it means for both sky fans and the metal and glass we have placed above our heads. Chapter 7. Dust Streams and Future Meteor Storms. Space is messy. Entropy likes a party. Every time a comet flares, it tosses glitter that does not get swept up. That glitter is dust, grains from sand, sized down to powder, that peels off the nucleus and keeps going on its own ticket. At first, the grains huddle near the parent path, like fans jogging behind a tour bus, but sunlight and gravity are patient sculptors. Over years to centuries, those grains stretch into streams that wrap around the sun like faint, spiraling ribbons. And if Earth happens to cut through one of those ribbons at the right time, the sky writes poetry with fire. Let us trace the life cycle of a grain. The moment it is lofted, it inherits the comet's speed and general direction, but it is not a perfect tag-along. Smaller grains feel a steady shove from sunlight that nudges them outward and slightly alters their track. Larger crumbs, being stubborn, stay closer to the parent lane. Imagine a river shedding tiny leaves and heavier twigs. The leaves drift toward the banks. The twigs keep to the current. Add in the sun's gentle drag that slowly reels particles inward, and you have a slow choreography. Out, then inward, then around, each size class carving its own braid within the larger stream. Grains do not spread randomly. They organize into trails. Think of each pass near the sun as a confetti burst. That burst becomes a narrow filament traveling just ahead of or behind the parent body. Over time, many filaments stack along the orbit like beads on a wire. The stream is not a uniform haze, but a necklace of dense lumps separated by quiet stretches. When our planet intersects a plain patch, we get a modest shower, the kind that rewards patience and a blanket. When we slice through a filament, all those grains arrive within a few hours, and the sky turns into a spark factory. That is a storm. Rates so high, you can almost feel the sky exhale. Prediction is part detective work, part weather report. Modelers take the parent body's path, rewind it for many cycles, and simulate the bursts from each return. They ask where those filaments will be during future Earth crossings and how the big planets might have tugged them into new lanes. Jupiter gets a special mention because it runs the outer neighborhood like a bouncer. A near miss can herd grains into clumps or spread them thin. In some lucky alignments, resonances lock grains into patterns that ride along with the giant for decades, turning a once modest shower into a once-in-a-lifetime pageant. Forecasts come with caveats, but the broad strokes are reliable enough that observers plan campaigns. And yes, a few weddings have been scheduled under predicted outbursts. Nothing says romance like interplanetary dust lighting your vows. What does a stream feel like from the ground? Picture the radiant, the point in the sky where meteors appear to fan out. It is an illusion from perspective, like train tracks meeting at the horizon. As Earth plows into the stream, particles hit the upper air at speeds that would make a sports car blush. Friction flashes them into brief lines and flares, each grain burning up long before it has a chance to kiss the ground. Faint streaks mark the smaller dust. Bright, sizzling events called fireballs announce the arrival of the bigger pebbles. During a storm, the count can rise from a few per minute to many dozens per minute, turning observers into kids at a fireworks show with infinite sparkles and no smoke. The romance has a practical side, because those same grains are not shy about bumping into our machines. Spacecraft at low and high orbits live in a drizzle of microhits all the time, but a dense filament raises the odds of a noticeable spray. Most grains are tiny, yet at orbital speeds, even powder behaves like a sandblaster. Designers fight back with layered shielding, sacrificial bumpers, and clever placement of fragile parts in the spacecraft's shadow. When an outburst is forecast, operations teams may pivot the craft to present a tougher face, delay sensitive maneuvers, or reschedule spacewalks. It is the orbital equivalent of turning your jacket into the wind. Satellites are not the only concern. Astronomers worry about the temporary increase in streaks across images and the chance of tiny pinpricks in delicate filters. Radio systems can notice brief hisses as trails ionize the air and reflect signals. None of this rises to movie-level hazard for a normal shower, but a true storm earns respect. The rule is simple: celebrate with your eyes, be cautious with your hardware. It is the same rule for birthday cakes and flamethrowers. Dust streams also carry memory. Grain composition preserves clues about the parent's layers at the moment of release. By measuring how fast meteors burn and what colors they flash, scientists back out densities and trace elements, turning the night sky into a disposable spectrometer. Over decades, repeated measurements reveal whether a stream is growing richer or washing out, hinting at whether the parent body is still active, breaking apart, or quietly coasting. Streams, in other words, are not only scheduled spectacles, they are long-running experiments that anyone with a lawn chair and a patient streak can help monitor. There is a long view here. Streams can endure long after their parent fades. A comet might fragment, retire, or drift beyond easy reach. Yet its dust keeps circling, paying ghostly visits every year or every few decades. Our calendars remember these lanes in names that return like holidays. When a newcomer from interstellar space lays down a fresh lane, we are essentially adding a future date to the sky's social calendar. Maybe a drizzle, maybe a showstopper. Entropy loves a party, but we love a program. So the next time someone shrugs at a comet and says, "It came and went," you can smile and answer, "It also left a message for later." We will check the inbox when Earth's orbit swings through that lane. Coming up next, we will switch vantage points entirely and watch from Mars, where orbiters and robots can capture angles and details that Earth can only dream of. Mars gets the balcony seats. Let us see what they reveal. Chapter 8. Mars gets the front row seat. If Earth is the cheap seat with a good view, Mars is the balcony box where the usher whispers. You can see the conductor's hands from here. When an interstellar comet threads the inner system, the fleet around the red planet becomes a chorus of specialized listeners. Orbiters carry instruments that do not care how romantic the comet looks. They care about how sunlight sculpts the fog, how gas peels away from the nucleus, and how those vapors mingle with the thin Martian air. The result is a vantage we cannot get from home, a kind of stereoscopic science where Mars provides the off-angle shot that completes the picture. Space agencies call it coordinated observations. I call it a cosmic symphony with excellent seats. Start with geometry, because the Martian vantage rearranges the lighting. From Earth, we often stare into glare, catching the comet head-on with the sun nearby in the sky. From Mars, the phase angle can be very different. Sometimes the red planet sits to the side of the action, so orbiters watch dust grains lit from the edge, a lighting trick photographers call rim light. Edge lighting makes faint structure pop. Filaments in the tail sharpen. Gentle fans from individual vents sift into view. If dust is the glitter of this show, side light is the flashlight that reveals where the glitter swirls and where it clumps. Suddenly, the choreography of jets becomes easier to map, like seeing footprints when the sun is low. Now to the instruments. Ultraviolet spectrographs ride aboard several orbiters, and they love comets because sunlight at short wavelengths snips fragile molecules and makes the fragments glow at precise colors. Those instruments trace water vapor, carbon monoxide, and carbon dioxide through their children and cousins, bright little fingerprints that tell who is evaporating and how quickly. Infrared spectrometers add the warmth map, showing where the coma is thicker and how dust grains of different sizes soak and release heat. A camera with a narrow filter sees the sodium whisper. A wide-field imager pulls the big picture, the entire tail curling like script across space. Each instrument is a section in the orchestra. Woodwinds for the gas, strings for the dust, percussion for the sudden outbursts when a crust patch gives way. A Mars orbiter can also perform a trick that Earth telescopes cannot. Limb scans through the cometary glow and the Martian upper air at the same time. When the spacecraft looks tangentially, it slices through layers, tasting both the coma and the top of Mars in one pass. If extra atoms drift into the planet's exosphere, the orbiter sees the faint brightening as a line in the spectrum. It is subtle, like hearing a triangle ping in the back row, but it tells you the comet's shed material briefly brushed the planet's environment. That is not danger. That is a tracer dye in a planetary wind tunnel. Then there are solar wind monitors and particle detectors. Some spacecraft at Mars watch how charged particles from the sun rattle the planet's bubble. Comets contribute their own stream of newly made ions, a kind of ghostly breath that gets picked up by the wind and swept into a narrow, straight tail. If the geometry is kind, Mars can sit near that lane and taste it. You end up with a portrait of two tails at once, the dust tail curling in sunlight, and the ion tail pointing like an arrow under the wind. It is the difference between confetti and smoke, both telling, both beautiful. Coordination is where the music truly swells. Picture an observing plan that staggers instruments like solos. One orbiter images the dust tail every few minutes for an hour, catching waves as the nucleus rotates. Another takes ultraviolet spectra at the same time, measuring how the gas flow rises and falls with the rhythm of jets. A third spacecraft skims the edge of the Martian atmosphere, checking for any temporary boost in glow lines as stray atoms drift down. On the ground here, at home, telescopes time their exposures to match. Now stitch the timelines. Peaks in dust brightness line up with spikes in gas emission. A faint glimmer in the upper air of Mars echoes those spikes a few hours later. You can almost hear the conductor count 4 and bring in the brass. Mars also offers parallax, the same trick our eyes use for depth. With Earth and Mars separated by a generous stretch, the comet's position against background stars shifts slightly for each observer. Combine the two views and you refine the path. That does not sound glamorous, but precision is the key that opens better physics. Better path means better speed. Better speed means cleaner subtraction. When you model how jets push the nucleus around, it is the celestial equivalent of tuning the piano before the concerto. Even the surface robots contribute in quiet ways. A rover's sky camera can catch the comet as a faint fleck near sunrise or sunset, allowing scientists to calibrate how dust in the Martian sky scatters light. That, in turn, tightens models of how sunlight would look passing through the comet's own haze. The red planet becomes a living laboratory for both the instrument and the phenomenon, like practicing your solo in a hall before the audience arrives. What do we learn from this balcony box that we could not from home? We learn which vents dominate the coma and how their directions shift as the nucleus turns. We learn the grain sizes in the dust tail by seeing how the edge lighting separates the fine from the coarse. We learn the gas budget, not as a single number, but as a daily rhythm that reveals crust strength and layering. We learn whether a planet's upper air even notices the passing whisper of atoms, and if it does, how long the whisper lingers. The lesson is that a comet is not just a picture, it is a performance, and Mars lets us sit close enough to read the conductor's notes. Next time, we will widen the pit and bring in the heavy hitters, the space telescopes, and the big ground arrays. When Hubble, Webb, and the rest play their parts, the symphony grows from chamber music to full orchestra, and the score turns from pretty to profound. Chapter 9, Hubble, Webb, and Friends, a multi-telescope blitz. If a comet is a touring band, the Global Observing Campaign is the world's most well-organized fandom. Space telescopes, mountaintop mirrors, backyard rigs, and radio dishes all show up with different instruments and the same intention: catch every note. Science is basically a group chat with better optics, and during a headline visitor, the chat goes into all caps, calendars sync, pointing plans shuffle. 1,000 small choices add up to one big story. Let us start above the atmosphere, where the two celebrity headliners live. One orbiting veteran brings the gift of crisp ultraviolet and visible images. Another, newer eye sees in infrared, turning the comet's warmth and chemistry into maps. Together, they act like two photographers shooting the same concert from different sides of the stage. One captures the sparkle of jets in scattered sunlight. The other records the heat of dust and the signature glow of gases that were invisible to the first camera. When they time their shots a few hours apart, we get a flipbook of change, how a fan-shaped outflow grows, thins, and tilts as the nucleus turns. Down on Earth, the big mirrors line up. Adaptive optics systems flex their muscles, ironing out atmospheric wiggles, so stars turn from twinkles into sharp points. A sharp star is not just pretty. It is a ruler to measure how fuzzy the coma truly is. Spectrographs split the glow into rainbows with surgical precision. In one exposure, you can read the fingerprints of water vapor, carbon monoxide, carbon dioxide, and a family of carbon-bearing fragments that act like neon signs. Polarimeters add another angle, measuring how light is oriented after bouncing off dust grains. That tells you if the grains are fluffy or compact, smooth or clumpy, and whether the coma is full of tiny powder or mid-sized crumbs. Imagine judging a beach not only by color, but by how the sand squeaks under your feet. The radio and millimeter crowd brings the backstage pass, arrays of dishes tuned to lines that trace specific molecules, including those that hide from optical light. These instruments do not care if the sky is hazy. They listen for whispers that slip through clouds. From them, we learn outflow speeds, which act like a speedometer on the gas, and we learn how gas and dust part ways as they leave the nucleus. Put those speeds beside the infrared maps, and you get both the traffic and the road. Throw in radar if geometry allows, and you might even ping the inner coma, teasing out structures near the core that are too small for any camera to resolve directly. None of this works unless the scheduling is smart. The comet moves, the sky rotates, the moon butts in, and weather does not read memos. So teams stagger observations. One site handles the early hours and then hands off to a night a few time zones west. Spacecraft slip exposures into their orbits, threading the gaps between other programs. Queue scheduling helps, with observatories reshuffling targets on the fly when a window opens or a cloud closes. The backstage drama is not glamorous. Spreadsheet cells, priority flags, a torrent of email, but it is the reason the public sees a seamless highlight reel instead of a patchwork. Calibration is the unglamorous hero. Before you can brag about a subtle color shift, you have to prove your instrument was not in a mood. Flat fields clean up pixel quirks. Standard stars set the brightness scale. Wavelength lamps make sure a bump in the spectrum is a real molecule, not a wandering grating. Cross-calibration meetings compare notes so that a green tint measured in Chile means the same thing as a green tint in Hawaii and on an orbiting platform. When 10 teams agree on the same story, confidence levels stop being hand-wavy and start being solid. Then comes synthesis. Think of a timeline with layers. One layer holds the crisp images of the inner coma, revealing jet geometry. Another holds gas production rates derived from spectral lines, rising and falling with the spin. A third layer maps the thermal glow of dust, showing where grains collect and cool. A fourth layer from radio dishes records the exhale speed. When you align the layers, patterns leap out. A spike in gas production might precede a brightening in the dust tail by a few hours, suggesting that fresh grains needed time to drift outward and catch sunlight. A recurring asymmetry in images might line up with a repeating feature in the spectra, revealing a persistent vent on one hemisphere of the nucleus. It is less like reading a single article and more like scrolling a live dashboard, where every graph is talking to every other graph. Public data portals have turned this into a spectator sport for professionals and amateurs alike. As reduced files drop into archives, small telescopes can pivot strategies the same night. If a spike appears, citizen observers tilt their rigs and extend sessions, feeding the machine with more time coverage. The chat grows again, now with annotated screenshots, mini light curves, and side-by-side stacks. The boundary between the big guys and everyone else fades, because when the target is changing by the hour, dense coverage beats fancy equipment 9 times out of 10. And yes, there is art in the output. Time-lapse movies show the coma breathing, the tail swaying, and the stars sliding by like a conveyor belt. False color maps turn invisible chemistry into glowing tapestries, where each hue traces a different ingredient. Even the most hard-nosed analyst will pause over a frame where a jet curls like calligraphy. Beauty does not replace evidence, but it does keep tired humans awake at 2 in the morning, and that counts. By the end of the Blitz, the comet is no longer a mystery guest. It is a character with habits, moods, and a paper trail. We know what it sheds, how fast it exhales, which side is shy, and which side loves the spotlight. The orchestra packs up, the group chat quiets, and the archives keep humming. The next team that wants to ask a deeper question will not be starting from a blank page. They will be starting from a symphony. Next time, we step into the post-concert debate. Is this visitor fundamentally odd, or is it a normal comet doing normal things very loudly at interstellar speed? Bring your best arguments and your calm voice. Chapter 10 is where the hot takes go for a cooling walk. Chapter 10, The Great Debate. Weird rock or normal comet doing normal things loudly. Every headline visitor earns 2 fan clubs. One says, "Behold the oddball." The other says, "Relax, this is textbook physics wearing a shiny jacket." Sorting those camps is not a shouting match. It is a method. You line up observations, you test simple explanations first, and you ask what new data would make one idea wobble. The question on the table is straightforward. Is this interstellar traveler a fundamentally weird rock, or is it a fairly ordinary comet, exaggerated by speed, lighting, and our limited vantage? As always, evidence gets the microphone. Start with the playbook for weird. Anomalies usually announce themselves in three ways: brightness that does not behave, motion that does not fit gravity alone, or spectra that refuse to match expected ingredients. If the object brightens or dims in a pattern that implies an improbable shape, the weird camp perks up. If the path seems to need an extra push beyond the sun's pull, ears prick again. If the glow lacks familiar gas fingerprints, more eyebrows rise. None of these are verdicts. They are clues that tell us where to point sharper tools. Now flip to the ordinary done loudly playbook. Comet physics is a surprisingly generous toolbox. Outgassing can mimic a small rocket thrust and gently tweak a trajectory. Dusty comi can boost brightness in unpredictable spurts. Rotation plus patchy activity can make light curves look wild without invoking exotic shapes. Even reflectivity can play tricks. Dark crusts, bright frosts, and evolving coatings can skew size estimates until you model them carefully. The ordinary camp asks, can standard ingredients and geometry explain the data if we account for speed and viewing angle? If the answer is yes, with reasonable parameters, that side rests its case for the moment. A crucial referee is parsimony. The simplest explanation that fits all the data gets first dibs. That does not mean boring, it means disciplined. Suppose the path shows a subtle nudge. Before we invent new physics, we test whether sun-warmed gases could produce that nudge at the measured activity levels. If the coma exists, if jets are visible, and if the calculated thrust is in the right ballpark, the ordinary thesis is strong. Only when the numbers miss by a country mile do we escalate to stranger ideas. Light curves are another arena where interpretations spar. A wildly varying brightness could imply an elongated, even pancake-like body rolling in the light, or it could be a roughly rounded nucleus with a few energetic vents that take turns facing the sun. Which is it? The tiebreakers are color and timing. If the swings coincide with gas or dust signatures, waxing and waning, activity is the likely driver. If the swings are color neutral and the coma looks strangely quiet, shape steps forward. Debates sharpen when teams compare independent datasets and find which explanation can match them all at once, not in isolation. Speed adds spice, but not necessarily mystery. Interstellar pace compresses time. Jets flicker faster in our observations, dust arcs stretch farther between nights, and small modeling errors blow up quickly. That compression can make familiar effects feel unfamiliar. Think of it as watching a normal dance routine at double tempo. Without rehearsal, it looks like a brand new choreography. The cure is cadence, dense observations that catch the object often enough to slow the story back down in analysis. Composition arguments often hinge on what we do not see. If some expected gases lurk below detection limits, the weird camp wonders about unusual chemistry or processed surfaces. The ordinary camp counters that dust can mask lines, sunlight can break molecules before they escape far, and instrument sensitivity matters. Here, multi-wavelength coverage is king. If a gas refuses to show in one band but leaves fingerprints in another, the mystery diminishes when nothing appears anywhere. Only then do we consider genuinely atypical ice recipes or crust histories shaped in a foreign nursery. There is also a meta question. How much novelty should we expect from the space between stars? On one hand, different birthplaces and weather histories should produce variety. On the other, planetary formation follows broad rules everywhere we have looked. The balanced stance is to expect familiar physics with local accents. A comet is still a comet, but its dialect, grain sizes, layering, trace compounds may carry the flavor of its home system. That stance keeps us cautious about declaring anything unprecedented until the evidence corners us. In public, debates pick up extra baggage because weird makes catchier headlines than standard model behaves nicely. Inside the community, the tone is calmer. Hypotheses are numbered, not married. Teams publish fits with their assumptions spelled out. Others try to break those fits by swapping parameters and seeing if the story holds. If an explanation survives contact with unfriendly tests, it earns confidence. If it fails, it gets revised or retired. Progress is less courtroom drama and more carpentry. Measure twice, cut once, test the joints. And yes, there is room for gentle humor while we work. Black holes delete browsing history permanently. Interstellar comets just clear cookies on the way out. The joke lands because it respects the stakes. We are not in a crisis, we are in a calibration exercise. A single flyby will not rewrite physics, but it can refine it. Each chart, each spectrum, each time-lapse adds weight to one side of the scale or the other. Where does that leave our visitor? In the productive middle? Intriguing enough to test our assumptions, cooperative enough to let standard physics explain a lot, and fast enough to make everyone drink more coffee. If future passes or sharper instruments reveal stubborn mismatches, motion that outgassing cannot shoulder, spectra that dodge every familiar template, then the weird camp gets its day. If not, we will have learned again that nature prefers simple rules with creative staging. Next time, we will trade debate for drills and look at what the encounter taught planetary defense, how detection networks rehearse, how decisions speed up, and how a harmless visitor can still upgrade our readiness for the day when the script is less forgiving. Chapter 11, Planetary Defense, learns new moves. An unexpected, fast interstellar visitor is not just a pretty light with a tail. It is a fire drill with stars. It sprints in, refuses to circle back, and asks one hard question: can we spot, share, and study fast enough to matter? Planetary defense used to be framed around stop the rock. Encounters like this add a second lesson: know early, decide fast. Even when there is no threat, the rehearsal upgrades the orchestra from the first violin of discovery to the timpani of decision-making. Start with the detection network, the early warning part of the story. Wide-field surveys sweep the sky every clear night, looking for anything that moves against the fixed tapestry of stars. The software compares frames, subtracts the steady wallpaper, and chains moving points into a candidate track. Most nights, this is routine housework. A fast interstellar target turns the routine into a sprint. The object brightens quickly, crosses huge chunks of sky in short order, and will soon be too close to the sun for comfortable viewing. The clock is loud. The mantra becomes simple and sharp. Detect, link, confirm. As soon as the first alerts go out, the data-sharing pipeline takes center stage. Coordinates and times flow to clearinghouses that everyone trusts. Observers on different continents immediately point their instruments and submit fresh positions. Those extra points tighten the path and chop down uncertainty. Think of uncertainty as a blurry cone that narrows with each new measurement. For a fast mover, you want that cone thin enough that even a small backyard rig can hit the target. The global handoff is like a relay, where the baton is a set of sky coordinates, and the finish line is a reliable orbit by morning. Rapid tasking of telescopes is the third movement, and it is a dance with logistics. Large observatories juggle packed schedules. When a rare target appears, coordinators shuffle the deck. Time-sensitive programs slide forward, flexible projects step aside. Robotic scopes jump first because they can pivot in minutes. Human crews follow with deeper exposures and specialized instruments. The goal is coverage across wavelengths and across time zones. You do not need one perfect image. You need a wave of good ones that stitch together into a timeline. Science is basically a group chat with better optics, and during a sprint, the chat window becomes a blur of timestamps, finder charts, and polite panic. Why does this matter for defense if the object is not a hazard? Because the mechanics are the same. The skill of turning a sky alert into a coordinated campaign is exactly what you need when the script is less friendly. Fast movers expose slow links, outdated email lists, bottlenecks in data formats, instruments that take too long to reconfigure. After the visitor leaves, those weak points become action items. Someone writes a better guide for how to format a position report. Someone else builds a shared dashboard that updates in near real time so teams do not trip over one another. In meetings, soon becomes a number of hours, not a fuzzy promise. Coffee is suddenly a mission-critical fluid. Decision speed is not only about telescopes, it is also about messaging. If there is even a whisper of risk, the public wants answers, and rushed answers can confuse. The cure is a playbook. Who speaks first? What phrases convey confidence without overreach? How to explain probability in plain words. During a sprint, communications teams practice this cadence even when impact is off the table. You cannot build trust on the fly. You build it during calm, so it holds during noise. One line that always helps. Here's what we know today. Here is what we are measuring tonight. Here is when we will update you. Clarity is the quiet superpower of defense. Another muscle that gets stronger is simulation. While the real object streaks by, analysts run parallel universes on their laptops. What if the same orbit was shifted earthward by a hair? How many days of warning would we have had? Which cities would have had the best view for tracking? Which radar facilities could have pinged it, if any? These counterfactuals are not morbid, they are maps. They turn a once-only event into a training set for future choices. The outcome is a matrix of go or wait rules. When to escalate to an emergency tasking, when to hold steady and watch, when to call partners and request international time on key instruments. Fast interstellar visits also stress the interfaces between science and operators. Satellite companies ask whether they should rotate spacecraft during predicted dust enhancements. Flight controllers for crewed missions want a yes or no on spacewalk timing. Meteor networks on the ground request forecasts for possible outbursts. None of these decisions are life and death for this visitor, but making them smoothly now means making them smoothly later, when stakes are higher. Practice turns hand-waving into checklists. Hardware takes notes too. During the scramble, teams discover which cameras overheat when slewed hard and fast, which filters produce the cleanest gas lines under rushed conditions, and which small scopes deliver the best value per minute. Later, these field notes turn into upgrades, better shutters, quieter cooling systems, software that autofills repetitive forms so observers can focus on the sky instead of paperwork. The lesson is not glamorous, but it is powerful. Readiness is built from dozens of small frictions removed. There is a cultural shift hiding in all this. Planetary defense used to be thought of as a rare, grim business. Now it looks more like a standing habit. Nightly vigilance, rapid collaboration, and humble postmortems that feed steady improvement. The interstellar visitor acts as a coach more than a villain. It blows a whistle, runs us through drills, and leaves us winded and better. And yes, the slogan matters. Know early, decide fast. Early means survey depth, smart pipelines, and automatic alerts that do not sleep. Fast means trained people, pre-approved playbooks, and tools that put the right plots on screen without a scavenger hunt. Put together, they form a kind of civic muscle memory for the planet. We do not need to be dramatic. We need to be ready. Next time, we will trade checklists for colors and turn to chemistry. How spectra from the coma let us read a slow-cooked recipe of water ice, carbon compounds, and dust, and what that says about where this traveler first learned its tricks. Chapter 12, Chemistry Class, but make it cosmic. Imagine walking into a kitchen where the chef refuses to speak, but the pantry labels are singing. That is what spectroscopy does for a comet. We cannot slice the nucleus or scoop its dust with a spoon every time, so we listen to light. Sunlight hits gases and grains around the traveler, and they glow in colors so specific that each one might as well carry a name tag. Chemistry here is just cosmic cooking with very slow ovens, and the recipe card is written in rainbows. First plate on the counter, water. When sunlight nudges frozen water into vapor, the molecules tumble and break into lively fragments that shine at telltale hues. Instruments split the coma's glow like a prism at a school science fair, but with grown-up finesse, turning fuzz into a barcode. From those lines we can count how much water is leaving the nucleus every second. That number matters because water is not just a drink, it is a storyteller. A strong water signal says the crust has cracks, or vents, that let warmth reach ancient layers. A weaker signal might hint at a dusty blanket keeping the cold heart insulated. Either way, the steam is a voice from the freezer telling us how the surface is built. Next, carbon dioxide and carbon monoxide, the early risers of comet kitchens. They escape at lower warmth than water, so they speak up first during the approach to the sun. If the spectrum shows a generous helping of these gases, we infer that the comet's outer layers are rich in fragile ices, the kind you would store only if your pantry never lost power. If they are scarce, maybe this traveler spent eons near a star and baked off the easy stuff. Or maybe it formed in a region where those ices were rare to begin with. Different pantry, different menu. The relative proportions of water to carbon species become a fingerprint of birthplace conditions, like tasting a stew and knowing which market the vegetables came from. Dust grains get their say in warmer colors and gentle glows you can feel rather than see. Tiny minerals and carbon-rich bits warm in sunlight and re-radiate that heat in long, soft wavelengths. Think of embers after a campfire, but stretched into a spectrum. The shape of that warmth curve reveals grain sizes and textures. Fluffy, porous dust radiates differently than smooth, compact crumbs. If the signature leans toward haze, we picture brittle crusts crumbling into powder. If it hints at larger pieces, perhaps cliffs are shedding pebbles, or the jets are gently sanding the surface. Either way, you end up with a tactile sense of a place you will never touch. The best part of this rainbow reading is how it reaches beyond the comet to the space between stars. Some of the simplest molecules in the coma are forged under harsh cosmic weather, and their survival or absence carries gossip about the interstellar medium. When we see certain fragile fragments thriving close to sunlight, we know the parent ices were shielded deep inside the nucleus. When those fragments are missing, but sturdier cousins remain, maybe the outer layers were processed by eons of radiation in cold darkness before the comet ever met our star. Light becomes an archivist, filing each clue under conditions of formation and conditions of storage. If you want a taste of deep time, listen for isotopic ratios, the subtle differences between a common atom and its heavier family member. We will not toss symbols around. Think of them as same fruit, extra seed. When the ratio of the heavier water flavor to the lighter water flavor is high, it whispers a formation story in colder, more remote nurseries. When it is low, warmer birthplaces get a vote. These ratios compare not just comets to other comets, but comets to oceans, to planetary atmospheres, even to the breath of ancient meteorites. It is a blind wine tasting where the sommelier is a spectrograph and the vintage is billions of years old. Sometimes the spectrum surprises with organic fragments, simple carbon chains that would burn to ash in a hot oven, but camp happily in a deep freeze. Their presence is not a headline about life. It is a headline about ingredients. A young planetary system is a kitchen full of starter kits, and comets are delivery trucks. Knowing which kits they carry tells us what raw materials were available on early worlds. If the mix is rich, the delivery route may have sprinkled that richness across many orbits, not just ours. Chemistry becomes logistics, and logistics becomes habitability. All this analysis would be dull if it was static, but the spectrum dances. As the comet turns, certain vents face daylight and others rest. Production rates rise and fall like a slow tide. Water might peak at afternoon on the nucleus, while carbon dioxide prefers the morning. and dust surges when a fragile patch crumbles. Time series spectra capture these rhythms and let us map active regions without seeing the surface directly. It is like hearing the melody of a music box and figuring out where the brass pins sit on the drum. Of course, light can mislead if you are careless. Sunlight not only warms, it also shreds. Some molecules break into pieces that glow so brightly they drown their parents' voices. That is why instruments span many wavelengths, from ultraviolet where breaking happens, to infrared where warmth speaks, to radio where cold gases whisper. If a line pops in one band and vanishes in another, we ask whether the comet changed or whether our lamp cut the cloth a different way today. Cross-checks keep us honest, and honest spectra keep the story straight. In the end, a comet's chemistry reads like a family recipe, carried across a continent. Familiar ingredients, local spices, and a few substitutions picked up along the way. Our visitor brings its own card, and the oven it used was time. We decode the flavors, compare them to our pantry, and sketch the grocery map of its home system. Next time, we will trade kitchens for pinball tables and follow gravity's nudges, asking how close passes with big planets can re-aim debris and trace new arcs without turning the story into fear. Chapter 13, Gravity's Pinball Machine. Picture the solar system as an arcade that never closes. The lights are distant stars, the playfield is a great disk of orbits, and the bumpers are planets with a talent for politely shoving anything that wanders too close. A comet drifts in, and suddenly the game begins. Gentle nudges here, a sharp kick there, and sometimes a clean redirect that sends the visitor down a lane no one expected. Jupiter is the bouncer of the outer solar system, and sometimes it redirects the line. The trick is to tell the story without turning it into doom. This is not fear, this is choreography. Start with a close pass, not a crash, because nearly all the drama happens without contact. When a small body approaches a big planet, it enters the planet's sphere of influence, a region where the giant's gravity briefly becomes the main voice in the conversation. Inside that zone, the comet is like a skateboarder, riding the curve of a ramp. It can exit faster or slower, tipped up or tipped down, depending on the angle of arrival. If it passes behind the moving planet, it can borrow a bit of the planet's orbital energy and leave with extra pep. If it passes in front, it can donate a little speed and depart more subdued. No engine required, just timing. Space invented cruise control long before we did. Those energy trades are the backbone of gravity assists used by spacecraft, but comets and boulders receive them for free and without planning. One small change in arrival time can flip the outcome from mild to memorable. A near pass might shift the path by a sliver today that becomes a grand reroute decades later. Think of a river current. Tilt a leaf by a finger's width at one bend, and you decide which bank it will brush a mile downstream. Planetary nudges are that finger. They do not rewrite the rules, they apply them. Now, let us talk debris. Comets vent gas and shed crumbs. During a near pass, the big planet does two things at once. It tugs the nucleus and it tugs the grains in the tail, but not identically. Larger pieces feel almost the same pull as the parent. Fine dust listens more to sunlight's gentle push. The mismatch spreads or focuses the cloud. You can end up with a dust lane that is tighter and brighter, like a stream pressed through a narrow canyon, or one that is stretched into a broader veil. In rare alignments, the planet's gravity can act like a magnifying lens, briefly concentrating particles along caustic curves. Fancy words for places where the traffic thickens. From far away, those thickened regions show up as knots and subtle fans that drift and dissolve as the dance continues. There is also the matter of resonances, which is a grand term for a simple rhythm. If a small object circles the sun in a time that fits a neat ratio with a planet's year, say every few laps it and the giant meet in roughly the same place, the repeated tiny tugs add up. Imagine someone pushing a child on a swing, always at the right moment. Over time, the arc grows. In space, the result can be sculpted lanes of emptiness and fullness. Certain zones grow quiet as objects are nudged away, while other zones collect followers like the wake behind a boat. The outer system is full of these rhythms, written in empty lanes and clustered crowds. Jupiter, again, deserves a spotlight. With its size and position, it works as both shield and shaper. Sometimes it deflects comets into the outer dark, reducing the chance that they drift inward for a while. Sometimes it steers visitors toward the inner regions, but on paths that are not aimed at anything in particular. Less often, it captures a wanderer for a brief season, turning a drifter into a temporary moon that eventually escapes, or, in dramatic cases, meets a final end in the clouds. The point is not to crown Jupiter as hero or villain. It is to recognize that the planet runs the door with a steady hand. Most guests pass, a few are redirected, and the bouncer never breaks a sweat. Saturn and the ice giants contribute with finesse. Their spheres of influence are smaller, but their placement matters for travelers that have already been curved once by Jupiter. A second nudge can straighten or accentuate the first, like tapping a spinning coin to keep it upright a moment longer, or to settle it sooner. Over millions of years, these layered nudges write the large-scale traffic patterns we see. Families of comets with similar tilts, belts of debris with defined edges, and peaceful gaps where repeated whispers have ushered the dust away. Gravitational focusing is another quiet player. When a stream of particles passes near a massive body, the ones on the interior side are pulled a bit more, the ones on the exterior a bit less. Downstream, the stream narrows a touch. For dust, that means a subtle brightening along the axis behind the planet. For a rain of meteoroids intersecting a planet's path, it means a slightly enhanced chance of strikes near the leading side. This is not catastrophe, it is seasoning. Like all good seasoning, you notice it more when you know to look. Importantly, these pinball effects do not demand melodrama. Most outcomes are gentle edits, not wild slings. The solar system is large, and time is lavish. A comet might get its path tilted by a few degrees, enough to change which constellations it will someday thread, but not enough to imperil anyone. Dust might be corralled into a lane that Earth will cross as a pretty shower a few winters from now. Debris might be cleared from a region that makes future planetary formation simulations match reality a little better. The arcade keeps humming. From a storytelling angle, gravity's pinball machine turns the outer system into a living workshop where small effects accumulate and structure emerges. You do not need a villain for drama. You need patience and a sense for rhythm. Watch long enough and you see echoes, lanes repeated, gaps carved, clusters shepherded. Each pass near a giant is a note in a slow symphony, and the score extends far beyond our lifetimes. So when an interstellar visitor glides by a heavyweight, we pay attention to the angle, the distance, and the timing. We model the new path, we check the dust, and we look for focused knots that might trace the planet's invisible hand. Then we go back to our long watch, because gravity prefers to write in cursive, and cursive takes time to read. Next up, we come home to the practical, what this drifting glitter means for our machines. In Chapter 14, we will step inside the engineering mind and ask how satellites and crew prepare for the space equivalent of a gentle sandblaster, and how smart design turns cosmic grit into just another Tuesday. Chapter 14. Spacecraft versus sandblaster. Imagine working outside while someone tosses handfuls of glitter at you from a speeding car. That is roughly what spacecraft endure when a dust stream thickens. Tiny, fast grains tapping aluminum and glass at speeds that turn powder into punch. Most days, the drizzle is gentle. During an active stream, the odds of a noticeable spray creep upward. Engineers do not panic, they prepare. The game is not fear, the game is margin. Start with what the grains can do. A particle smaller than a grain of salt hits a solar panel or a camera window, and the energy of that impact melts and vaporizes a speck of material. The result is a pit that looks harmless under a microscope, yet can scatter light lower the efficiency of a cell, or seed a crack over time. Larger flecks can dent radiator fins, chip paint, and pepper thermal blankets. Very large pebbles are rare, but rare's not never, so designs assume a few surprises over a long mission. Space is a patient sculptor. Every tap leaves a story in the surface. Crews in orbit face the same environment, with an extra twist. Spacesuits are personal spacecraft. The outer fabric is a layered shield that tries to do 3 jobs at once. It must shrug off micrometeoroids, keep oxygen in, and allow an astronaut to bend an elbow. Designers build those layers like a sandwich. The first layer takes the hit, shattering the grain. Middle layers spread the impact and trap fragments. Inner layers preserve pressure and keep sharp bits away from the bladder that actually holds air. It is clever and proven, but no one treats it as magic. When forecasts suggest a brisk stream, spacewalks slide on the calendar. Knowing when to wait is a form of bravery. Satellites defend themselves with a similar philosophy. Do not make one wall, make a few. Whipple shields named for the inventor, but let us call them bumper shields. Put a thin sheet out front, a gap, and then the main wall. A grain smacks the bumper, explodes into a cloud, and the cloud spreads before it reaches the second wall, lowering the punch. Bumper shields work wonders for small stuff, and slow the medium stuff. For the very fast and very large, the best defense is geometry. Keep fragile parts tucked behind tougher ones, and keep critical lines short, so a single puncture is not a single point of failure. Orientation is an underrated tool. When a stream is predicted, many spacecraft rotate to present their strongest face to the oncoming flow. Solar arrays may pivot edge-on for a few hours, trading a little power for lower risk. Telescopes may close protective doors, suspend mirror cooling, or park instruments in safe modes that tolerate a surprise tap. Antennas that normally point straight at Earth may angle a few degrees, balancing communication quality with a safer profile. These are not dramatic moves. They are polite adjustments that turn sandblaster into breeze. Operations teams also get very intentional about timing. Maneuvers that would have exposed tanks and valves during a dense hour are moved to a quieter hour. Spacewalks are rescheduled to days when the radiant of the stream is below the horizon for a longer fraction of an orbit. Sensitive calibrations that demand perfectly clean detector surfaces are postponed so that any fresh pits or dust-induced glints do not masquerade as real sky features. It is the orbital version of waiting out a gust before lighting a match. Sensors notice when the sky grows busier. Shielded microphones on some satellites listen for tiny pings. Current monitors on solar arrays see tiny steps as cells lose a whisper of output. Star trackers, the cameras that help a spacecraft know which way it points, may need extra filtering because streaks can confuse their algorithms. Software learns fast. If a star field looks noisy, the tracker switches to a mode that rejects streaky frames and leans more on gyroscopes for a spell. Old-school engineers call this good manners. When a friend is having a loud day, you listen a little harder and speak a little slower. Crewed vehicles add layers of caution that only humans would appreciate. Windows are beloved but vulnerable, so crews keep protective covers closed unless the view is essential. Hatches remain closed between modules during forecast peaks so that a puncture would not depressurize an entire complex. Sleeping schedules may even shift a little, so that the crew is awake during the most active hours, just in case an alarm needs attention. The most likely event is nothing at all, which is exactly the goal. Good safety feels like boredom. Down on Earth, flight rules get refreshed. Agencies publish notices to operators listing the expected timing of streams, their radiant directions, and any recommended posture changes. Commercial satellite fleets respond in batches, pivoting in waves so that networks stay online even while individual spacecraft duck. Insurance risk models take notes, and telecommunication providers prepare for slightly higher rates of temporary signal glitches caused when ionized meteor trails reflect and scatter radio waves. No apocalypse, just a few more blips to smooth over. There is also the small matter of lessons learned. After a busy period, engineers combed through telemetry for hints which materials shrugged impacts best, which coatings clouded faster, which instruments rode out the noise with grace. The quiet hero is often software. A well-written fault management system can distinguish between a real hardware failure and a brief dust slap, avoiding unnecessary safing that could cost science time. The next build rolls those lessons into tougher windows, smarter filters, and kinder algorithms. None of this turns space into a padded room. It turns it into a workplace with good habits. The risk never reaches zero, and it does not need to. What matters is proportional attention. When the sky's grit count rises, we behave as if we expected it all along. Because we did. That is the difference between drama and craft. Next time, we will close the toolkits and open the curtains on something less measurable and just as powerful: how one dazzling visitor can ignite public imagination, swell classroom enrollments, and send backyard telescopes blooming like wildflowers. Curiosity is contagious, and a good comet is a super spreader. Chapter 15: Public Imagination and the Renaissance Effect. Every so often, the night sky throws a party no one planned, and suddenly everyone is outside craning their necks like neighbors at a surprise fireworks show. A dramatic comet is that kind of uninvited celebrity. It does not just light up the darkness, it flips a switch in people. You can feel it at crosswalks and coffee counters. Someone says, "Did you see it last night?" And 5 strangers become a tiny astronomy club for the next 3 minutes. Curiosity spreads faster than solar wind when you feed it a good mystery. The first ripple is gear. Sales for modest telescopes and decent binoculars jump the way umbrellas do when a storm rolls over a city. But it is more than numbers on a receipt. Families pull old scopes from closets, clean the lenses with the reverence of archaeologists, and suddenly a driveway becomes a micro-observatory. Neighborhoods invent star parties without calling them that. Someone brings a thermos, someone brings a folding chair, and someone brings a phone app that labels constellations like subtitles on the sky. The comet is the headliner, but the side acts Saturn's rings, a rugged lunar crater, a cluster of blue stars, steel hearts too. People realize the universe is not a screensaver. It is a place, and they are standing on a balcony with a front row view. The second ripple flows into classrooms. Science teachers, who normally compete with buzzing phones, discover they have leverage. A bright visitor is a built-in hook, a natural reason to talk about light, motion, and how we know what we know. Homework suddenly involves going outside. Lab write-ups include drawings of a fuzzy head and a tail angled against a familiar streetlight. The questions multiply and shift in tone. The timid "what is that?" becomes the bolder "how do we measure that? And why does it change night to night?" A single object in the sky turns rote facts into lived experience, which is how knowledge sticks. Learning is not a bucket you fill. It is a fire you coax, and comets bring kindling. Universities feel the aftershocks a year or 2 later. Admissions counselors notice more applications with essays that start, "I set my alarm for 3 in the morning to catch the comet over the soccer field." Departments find incoming students asking to join research groups that build instruments or analyze data from survey archives. Internships that once drew a polite handful of applicants now require a waiting list. When a generation sees that discovery is not a distant museum, but a thing that happens on a Tuesday, more of them choose to be the ones holding the tools. Media and the arts ride the wave as well. Photographers chase the comet to remote hills and coastal cliffs and bring back images that make even experts pause. Painters lift the color palette of the coma for a series that hangs in a local gallery. A choreographer designs a piece where dancers unwind like dust filaments in a gentle breeze, and the program notes explain that sunlight can push a grain the way music can push a mood. Science leaks into culture not as a lecture, but as seasoning, and suddenly a wider audience knows that space is not a cold vacuum, but a stage with texture. There is a quieter shift at dinner tables. New questions slip into the usual rotation. Why do tails point away from the sun, even when the comet is leaving? How do we know it is not coming back? Did early humans see shows like this and tell stories about them? Parents who have not cracked a science book in years find themselves narrating simple models with salt shakers and napkins. A good question is a tiny gravity well. It pulls in more questions. An evening that might have ended with a scroll through forgettable posts ends with a plan to wake up early and catch the sky when the neighborhood is still asleep. Shared awe has a way of resetting priorities. Outreach groups sense the moment and scale up. Planetariums add extra shows. Museums host Ask an Astronomer nights, where there are no wrong questions and all metaphors are welcome. Libraries put telescopes on loan, like books. The boundary between expert and enthusiast blurs in the best way possible. A seasoned observer might spend an hour helping a kid align a finder scope, and in that hour, both feel like citizens of a larger project. Science is not a solo sport. It is a communal craft that invites apprenticeships in parking lots. Technology amplifies the Renaissance. Social platforms that are often noisy become, for a few weeks, useful classrooms. Amateur observers post time-lapse clips of the tail swaying. Meteor watchers share counts and sky quality notes. A teenager stitches together images from 3 nights and discovers a subtle change in color that sparks a thread about chemistry. The comments thread for once is kind, because awe is a great moderator. Even the inevitable myths and wild claims get corrected with gentle explanations and patient diagrams. The algorithm learns, briefly, that wonder has engagement metrics too. Economics notices, quietly but meaningfully. Small towns near dark sky sites see a weekend boom as people drive out to escape city glare. Shops sell out of red flashlights and thermoses. Campgrounds host impromptu midnight meetups that are equal parts science and campfire lore. Policymakers catch the hint and consider protecting more dark sky corridors, not only for romance, but for tourism dollars and shared heritage. The night sky becomes a resource you can choose to keep. Underneath all this is a change in posture. When people taste discovery, they walk a little differently. A toddler points to the moon more often. A middle schooler buys a used kit and tries to build a spectroscope from a cereal box and a broken disc. A retiree starts logging meteor counts at dawn. None of these acts look like a revolution, but together they tilt a culture toward questions. Black holes delete browsing history permanently. Comets just clear cookies on the way out and leave us hungry for better bookmarks. The comet, of course, fades. The world returns to alarms and errands. But the Renaissance lingers as habit. A few telescopes remain near the back door. A few students stick with the hard math because they remember a night when the sky rewarded patience. A few town councils pass lighting ordinances that make stars visible again. The ripple becomes a tide. Next time, we will ride that momentum into the workshop. How the rush to understand a rare visitor spins off technology, from smarter detectors to faster data pipelines, and why those upgrades end up helping everything from wildfire monitoring to medical imaging. Curiosity may be the spark, but innovation is the lantern it lights. Chapter 16, Tech Spin-offs. You did not see coming. A headline comet does not just light up the sky, it flips a switch in engineering labs. Overnight, perfectly respectable roadmaps become sticky notes, and the schedule transforms into an espresso-powered brainstorm. The scramble to study a fast, one-time visitor like 3IATLAS is a field test for gear and software, and field tests have a way of rewriting the future. The funny part is that the biggest winners are often nowhere near an observatory. One comet, many upgrades. Start with detectors, because every photon is a priority package. When a rare target brightens and morphs day by day, cameras need 2 things at once: speed and subtlety. Faster readouts catch the flicker of jets and the flutter of the tail, while lower noise teases out faint chemistry and delicate dust shells. That pressure has engineers pushing new sensor architectures that read small zones independently, so bright stars do not drown the coma, and the coma does not smear when the mount slews. Expect smarter on-chip tricks, dynamic range that expands on demand, pixels that switch gain like ears cupping for a whisper, and cooling systems that sip power while still tamping down thermal hiss. A side effect shows up in places you would not guess. Medical scanners that see more with less dose, traffic cameras that stop blooming in headlights, and wildlife monitors that pick out a hawk at dawn without turning the whole meadow into fog. Next comes the quiet revolution in optics. A comet with rapid variability exposes the limits of our glass. Coatings get reformulated to shrug off dew and dust while keeping reflections in check. Adaptive optics algorithms learn to converge faster, turning twinkly stars into sharp beacons in a few heartbeats rather than long, fiddly minutes. There is even renewed interest in rugged, transparent ceramics for protective windows, the kind of materials that do not flinch when micrograins nip at them. Give that a little time, and you will see the same durability in drone lenses that need to fly through salty spray, in factory machine vision that lives among metal shavings, and in rescue robots that crawl dusty stairwells without blinking. Now pan to the software, the brain behind the glass. A sprinting interstellar visitor is a stress test for tracking, so teams teach their models new moves. One family of algorithms learns to separate a fast, faint streak from a swarm of satellites and the occasional glinting airplane. Another learns to predict where the object will be, not just in the next frame, but also under different seeing conditions and with a different telescope altogether. These models start accounting for uncertainty in an honest way, not as afterthoughts, but as first-class citizens. The code then gets repurposed. Wildfire detection systems that have to tell smoke from cloud at twilight, coastal radars that must distinguish a fishing boat from a wave crest, and warehouse robots that track a package even when a forklift photobombs the scene. Think of it as a border collie for pixels, fast, faithful, and very hard to fool. Data pipelines are where all those upgrades meet reality. When a comet changes hourly, you cannot babysit terabytes by hand. The community leans harder into streaming architectures, alerts that flow in seconds, observations that auto-ingest with clean metadata, and dashboards that summarize without drowning. Old file formats give way to cloud-friendly layouts that let you peer inside giant archives as if they were local. That same machinery migrates into weather nowcasting, disaster mapping, and even sports analytics, where the goal is identical: pull the signal out of the fire hose while it still matters. Engineers like to say latency is a four-letter word. A good comet teaches them to bleep it out everywhere. Do not ignore the humble mount and the clever dome. Rapid follow-up means telescopes need to move like ballet dancers, not cranes. Expect lighter, stiffer structures that dive across the sky without wobble, paired with domes that open slats selectively to tame wind gusts, while still giving the optics a clear view. Pair that with smarter schedulers that juggle targets and weather like a seasoned air traffic controller, and you get more science per hour. The same control logic then slips into solar farms that must track the sun through gusts, or into stadium roofs that decide how to vent heat without dumping rain on the field. Engineering is a species that loves to migrate. Materials science gets a push from the dust itself. After an active stream, engineers examine pits and polish like forensic detectives. Out of those autopsies come new paints that do not chalk under ultraviolet, thermal blankets that resist micronicks, and laminates that fail gracefully instead of tearing. Some labs are playing with self-healing polymers that flow just enough to seal the smallest wounds when warmed by sunlight, the orbital equivalent of a skin that closes a scratch. Bring that down to Earth, and you have car windshields that repair tiny stars overnight, solar panels that heal pinpricks, and phone screens that laugh at pocket grit. Energy and autonomy round out the list. Chasing a dynamic target at odd hours means power budgets and onboard decisions get tight. Telescopes adopt edge computing, deciding in the moment which frames to keep and which to toss, which spectral lines to emphasize, and when to wake the high-power gear. The rewards are not confined to mountaintops. Remote sensors on farms can decide which rows need water without sending every frame to the cloud. Ocean buoys can choose to text home only when a storm grows teeth. Autonomy is thrift with manners. There is a cultural tech shift too. The Sprint normalizes open standards for alerts and metadata so that a small backyard rig and a flagship observatory can talk without a translator. That ethos ripples outward. City air monitors start publishing data in formats that plug straight into public dashboards. Conservation groups fold camera trap images into shared maps without wrestling with clashing templates. Interoperability may sound like a committee word. In practice, it is oxygen. If this all sounds like a hackathon lit by starlight, that is because it is. The visitor sets the timer, and in the rush to look up, we accidentally build tools that make everything else better. A comet is not a disruption. It is a rehearsal for competence. The sky hands us a deadline. We answer with upgrades. Next time, we will trade toolboxes for thought experiments. In the what-if files, we will imagine a once-in-a-century meteor storm, a tiny hitchhiker probe catching a ride, and a standing rapid response team that treats interstellar visitors like breaking news with rockets. Curiosity is the spark. Contingency planning is the bonfire. Chapter 17, The What-If Files. Let us open the drawer labeled Highly Plausible Mayhem, Low Anxiety. What if an interstellar object wandered into Earth's orbital neighborhood and decided to shed a few layers like a traveler, unpacking on the train, not a world-ending drama? No sirens, just a breakup that happens near our lane around the sun. The pieces would not fall straight down. They would spread along the parent path like glitter spilled on a moving conveyor belt. Weeks or months later, our planet could plow through that fresh ribbon and light the sky in a storm so intense that clocks would seem to run on streaks. You would step outside, and every few heartbeats the sky would draw a new white line, then another, then many at once, a celestial typewriter that forgot to rest its fingers. What would that mean on the ground? City dwellers would finally see a show that laughs at streetlights. Rural skies would look alive. Photographers would run out of superlatives and memory cards in the same hour. It would be the rare night when everyone agrees to look up, because looking down would feel like ignoring the ocean at the beach. On the practical side, spacecraft operators would rotate vehicles like hedgehogs showing their spines, and aviation would quietly tweak routes and radio strategies to dodge temporary hiccups. The rest of us would make tea and promises to remember this night forever, and for once we would keep them. Now, rerun the tape with a twist. What if we were ready to tag a visitor before the spectacle? Picture a tiny hitchhiker probe, no heavier than a carry-on bag, riding a modest rocket into a transfer that puts it near the object's path. It would not try to land. That is like jumping onto a moving horse while blindfolded and complimenting the saddle. Instead, it would fly beside the visitor for a few hours or a single day, sipping data with the calm of a field biologist. A handful of instruments would do the work: a camera with eyes for texture, a mini spectrometer to taste the gases, a dust counter to feel the breeze, and a beacon to send it all home. Could something that small matter? Absolutely. The secret is proximity. From Earth, a comet's head is a fuzzy lantern. Up close, the coma is a curtain you can part to glimpse vents, cliffs, and boulders. A brief side pass at a respectful distance would turn guesswork into geometry. We would measure the rhythm of jets directly, catch a chunk in the act of leaving, and read the menu of ices before sunlight shreds the labels. Scientists would dine on that data for years, crafting models that translate distant glows into surface maps. Engineers would raid the sensor designs for Earth jobs, because that is what engineers do when an instrument proves itself under pressure. How would we get a hitchhiker out the door in time with a shelf-ready kit and a playbook that assumes the universe does not wait? The kit sits in a clean room already fueled and tested. The playbook reads like a recipe that lists every step and every phone number. When the alert comes, hardware moves to the pad, software loads a target file, and the schedule shrinks from months to weeks to days. It sounds wild until you remember that weather agencies routinely launch emergency balloons and wildfire crews stage gear long before a spark appears. Space just asks us to bring that mindset above the clouds. Now let us go bigger. What if interstellar drop-ins become common enough that we stop calling them rare and start calling them seasonal? In that world, we would build a standing interstellar rapid response team. Imagine a permanent small mission line, a few nimble spacecraft parked in useful orbits, solar sails that can pivot like ballerinas, and a command center that looks less like a movie set and more like a cross between a newsroom and a laboratory. The team would carry a menu of actions. Option 1, immediate tracking and global alerts. Option 2, quick spectroscopic profiles from space and ground. Option 3, dispatch a hitchhiker for a side pass. Option 4, if the visitor's shy, move a sailcraft across its projected lane and let the dust do the visiting. The team would live on drills. Once a month, they would run a fake alert end to end, coordinate observatories, generate a shared timeline, post public updates in plain language, and archive results where a student halfway across the world can find them. The point would not be glamour, it would be rhythm. Know early, decide fast. If the object flings a dust ribbon that might make for a storm years down the line, the team pins that date on the global calendar. If a pass near a giant planet promises a dramatic change in path, they publish a memo that says, "Watch this lane in 5 years, it will be interesting." What would the rest of us notice? Better wide-field images in our news feeds that actually explain what we are seeing. Fewer rumors, more clarity. Citizen science portals that invite you to aim a backyard rig at a target that truly needs your help tonight, not sometime soon. And, in schools, a generation accustomed to the idea that discovery is not a once-a-decade postcard, but a steady stream of messages you can learn to read. These what-if scenarios do not ask for the moon, they ask for habit, foresight, and a willingness to treat awe as a resource worth planning around. The sky will keep sending unscheduled invitations. We can respond with a shrug, or we can respond with ready hands and good tools. The difference is not money alone. It is attention shaped into capability. Next time, we will let the curtain fall with grace. In the closing chapter, we will gather the lessons before the lights go out. What this visit taught us about seeing faster, thinking together, and listening for the next knock on the door of the solar system. Chapter 18, The Exit. Lessons before the lights go out. There is a moment at every great concert when the house lights start to rise, and you realize you are leaving with more than the ticket stub. Our interstellar traveler is already dimming, slipping back toward the quiet between stars, and the temptation is to count only the photographs and the headlines. But the real souvenirs are habits we did not have before. We learned how to listen faster, look deeper, and collaborate wider. Earth is still the rock that won the cosmic lottery. Now we are finally reading the fine print on the ticket. Call it NASA Science +1, science plus the muscle memory we built along the way. Listening faster began as a necessity and became a style. When the first alerts whispered that something odd was crossing the grid, we shaved seconds from every step. Software learned to thread moving points together without tripping over satellites. Observers traded the old rhythm of wait for confirmation for a new rhythm of confirm while you listen. It was not recklessness, it was tuned attention. The sky does not speak in complete sentences, it sends fragments. We practiced hearing them in order and answering in time. Looking deeper meant choosing patience over polish. We did not aim for a single perfect portrait to hang in a museum. We aimed for an honest diary, night after night, angle after angle, the glow recorded in ways that made change the main character. That diary taught us that a faint shrug in the tail, could be as telling as a bright flare, that colors we once dismissed as camera moods were in fact the comet cycling through its own weather. Plants like to say they invented solar panels first, comets countered with special effects, and we finally learned to read the credits. Collaboration went from helpful to unavoidable, and that is a compliment. No one instrument, no single hilltop, no single agency could hold the whole story. We stitched together timelines like a quilt, each square labeled and aligned so the seams made sense. A graduate student's spectrum in the pre-dawn hours matched a radio trace from a cold valley half a world away. A backyard rig added a few precious positions that tightened the orbit just enough for a larger facility to nail the next window. Science has always been a group chat with better optics. This time, the chat learned to keep tempo. Humility came bundled with the data. The visitor refused to be exactly what anyone first expected. It was neither pure spectacle nor stubborn enigma. It was a working object, shaped by time and sunlight, with a few quirks that made us argue just enough to improve our arguments. Black holes may delete browsing history permanently. Interstellar comets, just clear cookies on the way out. And in the empty cache, we found the discipline to check assumptions twice. We became careful with words like unprecedented and comfortable with phrases like consistent with. That is not timidity, that is craft. We also rediscovered that safety is not a switch, it is a posture. Even with no threat on the table, the rehearsal mattered. Schedules flexed, instruments safed and unsafed with grace, and messages went out in language that made sense to anyone with a sky above their head. Know early, decide fast is not just a planetary defense slogan, it is a way to respect the public's attention. Tell people what you know, what you are measuring next, and when you will be back. Keep promises. Repeat. If the comet had a legacy vote, it would probably pick the technology that grew up around it. Detectors learned to whisper and shout on command. Algorithms quit panicking at streaks and started seeing through them. Domes turned into dancers. Materials shrugged when dust tapped their surfaces. The way a good jacket shrugs off light rain. These are not toys for astronomers alone. They will turn up in ambulances, on farms, in cameras that watch forests and bridges, in sea buoys that text home when a storm sharpens. A bright visitor at the edge of vision can improve a tool you will never associate with the night sky. That is the quiet miracle of curiosity. You tug one thread and the sweater warms everyone. Culturally, the glow outlasted the glow. Driveways became observatories. Schools smuggled wonder into homework under the respectable labels of observation and report. A small surge of students decided to chase problems measured in light and time. Cities flirted with darker nights. Families found the good question can outshine a screen for at least an evening. The comet will not remember us, but we will remember what it felt like to look up together and treat the universe as a place we share, not a wallpaper we ignore. And now the lights really are rising. The traveler heads for distances where our best mirrors cannot coax a signal worth the lost sleep. The tale dwindles to a rumor. The coma dissolves into arithmetic. But absence is not erasure. Trails of dust remain in the lanes it traced. Datasets sit cooled and tidy in archives, waiting for the next clever question. Ideas drafted under pressure wait on shelves, ready for the next alert. We are leaving with more than photographs. We are leaving with readiness. So we let the stage clear with gratitude and a plan. The next surprise will arrive speaking with a slightly different accent. We will hear it. We will answer. We will improve again. Earth will still be the rock that won the cosmic lottery. And we will keep reading that fine print, one clause per sky event, until the whole ticket makes sense.